Okay, this will be the lecture for chapter 34. We'll be talking about optics. What we're going to start off with is talking about just how a plane mirror works, and then we're going to have curved mirrors. These guys are going to form images. It turns out that lenses can also form images, and really most of the physics that we're going to talk about is going to be in this section right here. Then what we're going to do is we're going to start stacking lenses together and talk about how camera works, how vision works, how we can use eyeglasses, lenses to correct our vision, simple magnification such as microscopes and telescopes. Let's consider light rays coming from just a point source. So we could be looking at some object at point P, and this object is going to be illuminated by sunlight, or you could say, hey, we're looking kind of at a candle or a light bulb or something like that. The light rays are going to radiate in all directions, so you can kind of imagine having infinite rays kind of coming off this point P in all directions. Now what's going to happen when they approach a plane mirror is they're going to essentially be reflected. And the law of reflection says, hey, you can go ahead and you can draw your angle right here, and that angle right there is going to be the same. So theta in is going to be equal to theta out. Now, this person's eyeball, however, is going to see in a straight line. So there's going to be, let's say, some ray that radiated out from point P, and that's going to enter the eyeball, so we're seeing an image. However, the eyeball is going to think that it came from a straight line, so it's going to appear as if there's an image behind the mirror. One thing to talk about for real images and virtual images is a real image is going to have a ray that approaches the surface and then reflects back and goes through point P. So this image that this person sees is going to be a real image. Now we can complicate things by talking about refraction. Light is going to behave in the same way. It's going to radiate in all directions. And if we're, say, looking at a fish in water, and we're out here in air, so the index of refraction is larger in the water, then the light rays are going to bend away. So we're going to have the light rays kind of go like this, and we're going to have a light ray approach our eyeball, and again we're going to see in a straight line, so we're going to think that there is an actual image right here, and we're going to denote the images by the primes. Objects are going to be denoted without a prime, and in this case right here there is no ray that passes through the object point P, so this image is going to be a virtual image. So let's come back to our point source, talk about just the plane mirror. Again, we're going to kind of have our eyeball right here, and we're only looking at the one single ray that this eyeball is going to see. And again, that person is going to think that there's an image right over here. Let's talk about distance for a second. We're talking distance to the object. It's going to be that distance right there. This is going to be the distance to the image, again denoted by that little prime on the S. And the question is are these positive distances or are these negative distances? So the object distance is going to be positive if it's on the same side as the incoming light. The image distance is going to be negative here because it's not on the same side as the outgoing light. So image goes with outgoing and object goes with incoming. So this image distance here is going to be negative. Let's take a look at the case of refraction. Here we're talking about some distance. Again, it's going to be denoted by the S, and that's going to be positive because it's on the same side as the incoming. And here we have our image right here, and here it's not on the same side as the outgoing light, so the image distance is actually going to be negative. You can kind of convince yourself by looking at this triangle right here and this triangle right here and saying that they're similar triangles. So in the case of a plane mirror, this object distance is going to be the same number as the image distance, just the image distance is going to be negative. For physical objects inside of plane mirrors, it's very similar to point sources. Here we're going to have object distance and image distance, and keep in mind that object distance plus image distance is going to be equal to 0 because the image distance is going to be negative. We end up with a series of similar triangles here, and you can kind of see that the object, which is just this arrow, You can kind of draw a ray just like that. It's going to be seeing itself, and it's going to be virtual because it doesn't actually exist. It's going to be erect because it's pointing in the same direction as the object, and it's going to be reversed. I'll talk about that on the next slide. Something else to talk about is going to be lateral magnification, which is going to be the image height divided by the object height. In the case of a plane mirror, this is simply going to be equal to 1. As promised on the last slide, we all know that if you look into mirrors, the handwriting is going to be reversed. So there's going to be kind of a left-right reversal. You can kind of see in the image right here that the writing hand is backwards. Also, if you take a look at this object in the image, the thumb has been reversed. We can also have multiple reflections. Suppose we had a point source right here at P, and so it's sending out rays of light. Here it's going to bounce off of mirror 1. It's going to then come and bounce off of mirror 2, and this one's going to do the same thing. And since my eye is going to see in straight lines, it's going to see this image P3 right here. But keep in mind that there's going to be two other images. There's going to be the image of P1 from mirror 1, but also there's going to be the image of P from mirror 2. So we get 3 images from having 2 mirrors. Now what happens if the mirror is curved? Let's just say it's going to be spherical just for the sake of simplicity. It's still going to obey the law of reflection. If we have some point P that's sending out light and it's reflecting off of the mirror, then it's still going to have, the angle in is going to be equal to the angle out. However, it has this distinguishing feature in that the mirror is bent, and we characterize that with a radius. We say kind of that this mirror, if you kind of continue this circle all the way around here, then it's going to have some center point C, and it's going to have some radius r. In the case where the curvature is on the same side as the light, then we're going to define that to be r to be positive. That's going to be a concave mirror. If the mirror is bent the other way, it's still going to obey the law of reflection. That angle in is going to be equal to the angle out. But now the radius is going to be negative because it's on the opposite side of the light, and this is going to be called a convex mirror. We can still kind of draw this out and say here we're going to have our point object, angle in is going to equal to angle out, and we're going to have some image right here, P prime. We're still going to define object distance S and image distance S prime, and we carry the same notation because they're on the same side as the light. Both of these guys are going to be positive. Just a very quick aside on the Hubble Space Telescope here. These images can be quite sensitive to the radius of curvature. If you take a look at this mirror down here, it has quite a large radius, but still is only off by 1/50th the width of a human hair. The original image of, say, a star right here looks quite junky. You see all this kind of trash out here. With some corrective optics, you can see extra stars right down here and here and here. Another interesting concept to consider when we talk about curved mirrors is going to be the idea that we can have a focal point and focal length, and really this is going to be how parallel rays that are incident on the surface are going to behave. If we consider parallel rays coming into this curved mirror, we would essentially say that the object is located at infinity, and you can kind of convince yourself that the law of reflection is going to apply. Angle in is equal to angle out for each and every single one of these rays. You can see that they all point to a certain point. This is going to be called the focal point. The distance from the focal point to the surface of the mirror is going to be called the focal length, which is denoted by a little tiny l, or a little tiny l with a little tiny f, and that's also going to be the image distance. Now we can say that the focal length is going to be related to how curved the mirror is. The more curved, the closer the focal point is going to be in, and really it's just going to be half the radius of curvature. You can also kind of convince yourself that if you had an object that is emitting light, it's emitting light in all directions at the focal point, that the same thing is going to, these rays can be essentially traced backwards, and we can get parallel light coming outwards. In this case, the image would be at infinity. We can, of course, extend this for physical objects, so we'll consider an arrow, and we'll just say this arrow is being illuminated by light, and so it's light's coming off of it in all directions. Now let's take a look at how it interacts with this curved mirror right here. We can essentially draw a nice convenient ray right here. It's going to bounce off the surface, draw my normal line, and you can convince yourself that theta in is equal to theta out. And so this ray is going to continue in this direction right there. That is at the tip of the arrow. Now if we took another ray and it passed it through the center of curvature, this is going to essentially come in normal to the surface and bounce off the surface, coming right back to the very tippy top of the arrow. It turns out that the intersection of those two lines is going to be where the tip of the image is formed. So you can kind of see that we have the image drawn right here, or the arrow. We have the object position, we have the image position. Both of these guys are positive because they're on the same side as the light. And also we can see that we have some image height that is now slightly different than the height of the object. So the magnification again is going to be the object height divided by the image height, and it's going to be negative object distance divided by image distance. In this case, you can see that y is going to be positive because it's in the positive direction. You can see that y prime, the image height, is going to be in the negative direction. A negative magnification means that the image is going to be inverted. Because the image is also smaller than the object, we would say m must be less than 1, or m must be less than -1. A very important equation which is going to relate the object height to the image height to the focal length and the radius of curvature is kind of written right here, where we say 1 over the object height is going to be plus 1 over the image height is going to be 1 over the focal length. Because we know the relationship between the focal length and the radius, we can also write it as such. Now it turns out if you move an object inside of the focal point of a concave mirror, then it's going to magnify it rather than make it smaller. So let's take a look at example 31.4, where we have an object that's 10 centimeters away from the mirror. So that's going to be our object distance, 10 centimeters. We're looking for the height on the screen. We also don't explicitly know the radius of curvature. We know the object height. So let's go ahead and say, well, what can we solve for? First, we can go ahead and solve for the radius of curvature. We can say that this object distance is 10 centimeters, so it's going to be 1 over 0.1 meters. We know that the screen is going to be 3 meters away, so 1 over 3. That's going to be equal to 2 divided by the radius of curvature. So that says that the radius of curvature is going to be 2, 1 over 0.1 is going to be 10, you add a third to that, so 2 divided by 10 thirds, that's going to be roughly 0.19 meters, so we've solved for the radius of curvature here. Now let's take a look at the magnification. The magnification is going to be negative object distance divided by image distance, and we know that the object distance is again 0.1 meters. Image distance is going to be 3 meters. Don't forget my negative sign. So you can see my magnification is negative 30. It has no units associated with it. It's just a number. And lastly, we can also say the magnification is going to be equal to the image height divided by the object height. So that tells me that my object height is going to be equal to the magnification multiplied by the object height. So negative 30 multiplied by the height of the object, 5 millimeters. I'm just going to leave it in the units of millimeters. So negative 30, that's going to tell me that's going to be negative 150 millimeters. What that negative sign right there means is that the image is going to be upside down.